Hello everyone, I am Kyoung-Hee Kim, a professor of architecture at UNC Charlotte. We will focus on BIPV design principles of renewable energy building integration. Before we move to our main content, here are a couple of reference books that you may want to check out for more details. Integrating solar systems is an integral part of net zero architecture toward the carbon neutrality goal. It makes use of otherwise underutilized surface area and can offer environmental and economic benefits due to their multiple functionalities. BIPV building enclosures reduce building energy use and offset energy consumption by generating power on site, curtailing the building's draw from the utility grid and its carbon footprint. Solar power generation coupled with battery storage can help supply a building's peak cooling loads, easing stress on the electric grid and enhancing energy resiliency. Continuing our focus on solar facades, there are two primary ways solar technology is applied to building facades. The first application, as shown on the top of the figure, is transparent or semi-transparent PV glazing. The second is opaque PV cladding panels, as shown at the bottom of the figure. For glazing applications, PV systems are embedded in glass units, such as windows and skylights. If solar panels are installed in front of the glazing unit, they act as solar power generating shading devices. Their translucent solar cells can be integrated within the exterior glass of the window unit, still offering views out and daylight penetration while producing solar energy. The third and fourth glazing applications are closed cavity facade systems and double facade systems respectively. Solar systems are installed in an air cavity where they are protected from dust, rain, and excessive heat buildup. The figures here illustrate opaque wall and roof applications. The solar systems can be integrated into the opaque wall system as a cladding system in the first case, or as a rain screen system in the second case. Roofs of low-rise buildings are also incorporating solar panels as roof cladding or as a trellis that provides shade for users on occupiable roofs. This slide explains a concept diagram of solar facade design. When designing a solar glazing application, it is important to balance solar power production performance, user experience, views, and aesthetics of the design. For example, BIPV integration happens in the upper and lower zones of the window unit, whereas the middle zone has a larger transparency for view out and daylight. It underscores how solar facade harmonizes performance, aesthetics, and user experience. There are different design strategies for solar facades depending on design expression, spatial effect, and performance goals. I will quickly go through the table on the right side. The egg-crated solar facade utilizes a grid-like structure combining horizontal louvers and vertical fins. The tilt angles and depth of the louvers and fins vary depending on geographic locations, facade orientations, shading needs, and thermal control requirements, while also enhancing user experience and reducing glare. Folded solar facade has distinctive origami-looking creases. It creates rippling effect across the building skins and distinctive visuals highlighted by dynamic shades and shadows. The angle and projection of the folding can be adjusted to balance solar harnessing, shading, and reduced glare. Layered solar facade places an additional solar layer in front of the primary glazed skin. This adds depth and a rich overlapping effect, enhancing insulation and energy capture. The extra solar layer also acts as a shading device and filters daylight. Relief solar facade employs recessed or raised parts, creating a three-dimensional texture. These indents and protrusions provide self-shading, cooling, and power production through depth and angles. Scalloping solar facade features tessellated patterns that can divide building enclosures between solar panels and non-solar panels. Solar panels capture sunlight at diverse angles and orientations while providing a calm and organic interior ambience. Shifting solar facade uses static or kinetic sliding panels to create playful interior lighting and shadow effects. Shifting panels could be statically aligned or kinetically moved, which creates playful light and shadow spatial effect. This shifting solar facade not only maximizes solar access and energy efficiency, but also enhances user experience. Staggered solar facade features a staggered geometric layout between solar panels and non-solar panels, creating a dynamic aesthetic and spatial diversity. This staggered composition maximizes solar harvesting while minimizing self-shading through diverse visual elements. Finally, terraced solar facade creates cascading balconies integrating with solar panels. The terraced configurations cascading effects of shade and light. The solar panels are tilted to receive the most direct sunlight while promoting rainwater harvesting. Overall, BIPV turns a building into a localized power plant without compromising building performance aesthetics. Now let's look at each design. The first example is Hanwha headquarters in Seoul, Korea. The facade has been retrofitted with egg-crated solar facades that create a sense of rhythm and texture. This egg crate strategy blends form and function in perfect harmony. Each rectangle frame of the facade curtain wall is precisely angled and placed with multiple intent of harvesting solar energy and enhancing the interior spatial effect. On the southern sides, where the sun is strongest and the solar angle is high, the panels project outward like horizontal louvers, their upper surfaces tilted to capture sunlight head-on. On the eastern and western sides, where the solar angle is low, the side verticals or side fins are more pronounced to block sunlight while generating power. The egg crate solar modules respond to the interior programs and sun path. The designers created program transparency. For example, larger openings where work areas need views, light, and an insulated pattern where privacy or shading is paramount. The solar modules create uniform light and reduce glare. The Federation of Korean Industries FKI Tower in Seoul integrates a folded facade that recalls the creases of origami, giving the high-rise a bold sculptural identity. Solar panels are integrated within angled, folded spandrel glazing, creating a dynamically rippled facade. The folded solar facade is both purposeful and visually distinctive. Each fold is calibrated to optimize solar conditions. The solar panels at the slab level are tilted about 30 degrees upward toward the sun to maximize solar energy capture via the integrated photovoltaic spandrel panels. Meanwhile, the transparent vision panels are underslung downward by 15 degrees, which provides self-shading and reduced direct solar penetration and glare for occupants. Inside the tower, the folded facade illuminates the interior with diffused daylight instead of strong, harsh sunlight. Glare is not an issue with the underslung vision panels during most of the day, except sunrise and sunset hours. Users can leave blinds open and enjoy the city views. The Glassbel office building in Klaipėda, Lithuania, features a layered solar facade installed as a secondary skin. This layered solar facade overlaps photovoltaic glass panels with the primary building skin as a layered double skin facade system. The double skins filters daylight, creates a sense of facade depth, and preserves unobstructed views. The ventilated cavity between the primary building skin and the secondary layer serves multiple functions of an insulating buffer against heat, weather, and sound, with strategic external shading that increases comfort within the building. The layered solar facade achieves dynamic architectural expression and enhanced spatial quality, balanced with improved environmental buffering and clean energy performance. This slide exemplifies the relief strategy at the Copenhagen International School. The recessed and protruding solar panels create a facade rich in depth and colors. They mimic the movement of ocean waves with the constant changes of shadow and light. The articulations of solar panels layout results in a three-dimensional solar surface. Some solar panels are set deeper, while others jut out at a slight angle, resulting in a three-dimensional solar surface. the solar panels provide self-shading with dynamic visuals, which keep the exterior microclimate cool. The three-dimensional surface encourages air movement surrounding the building to remain cooler. This illustrates a harmonious blend of site context, architectural beauty, and energy performance in the building. This slide exemplifies the scalloping solar facades at the Denver Botanic Garden. The building skins are ingeniously designed to harness sunlight, support the Botanical Gardens program, and showcase both beauty and performance. The building skin features hexagonal tessellated facade on pyramidal building mass, dividing solar panels, opaque wall, and skylight. Solar panels are strategically, performatively positioned within the hexagonal patterns. The scalloping solar system within the hexagonal patterns generates solar power while providing good insulation for energy savings in the process. Architects accomplish this by devising different design concepts that receive maximum sunlight and their penetration into the building while making the building visually appealing. Next is the shifting solar facade. The interior of La Seine Musicale in France integrates sliding solar shells that follow the moving sunlight for solar harnessing while filtering the sunlight. This sliding arrangement creates ever-changing patterned light and shadow inside the building. The shifting solar facade strategy uses panels on a building's exterior that are slightly offset from the primary skin and move along the movable track. This sliding movement gives the facade a dynamic, textured interior atmosphere, choreographing a lively play of sunlight, much like the way sound dances through La Seine Musicale, a music hall in France. In net zero building design, strategies like the shifting solar facade beautifully balance form, function, and experience. They make structures visually striking, energy efficient, and pleasant to occupy, showcasing how energy-generating facades can keep us cool and well lit while looking stunning in our cities. The Baoding Xushui Substation's staggered solar facade in China showcases vertical and horizontal shifting photovoltaic panels. This pattern creates a dynamic visual rhythm on the building skin. This alternating panel is positioned to maximize solar access and reduce self-shading. Inside, this staggered design generates ever-changing spatial quality and fills the interior with dynamic daylight, creating a lively ambience. Technically, the misaligned panels are oriented to seamlessly blending innovative design with interior comfort and sustainability. At the Baoding Xushui Substation in China, a staggered solar facade typology transforms a functional facility into a dynamic work of architecture. The SIEEB building in Beijing in this slide exemplifies a terraced solar facade with its floor plates stepping back like a series of traditional Chinese rice fields. The wide terraces are lined with greenery and solar panels. The terraced solar facade is in cascading balcony levels that recede as the building rises. The recessing balcony not only provides full solar exposures, but also allows sunlight to penetrate further into the interior and illuminate multiple levels as the day progresses. On each stepped-back terrace, the solar louvers are installed at certain angles, responding to the optimum solar exposure. This allows not only power production, but also provides self-shading during summer while capturing winter sunlight. The stepped terrace further promotes sustainability by directing rainwater toward collection systems, offering terraced gardens that alleviate reduced stormwater runoff while cooling the building. From an aesthetic perspective, the solar terraces create distinctive building features, enhancing clean energy visibility and user experience. This video was supported by UNC Charlotte in collaboration with the US ASEAN Smart Cities Partnership. For further inquiries, please contact Kyoung-Hee Kim at UNC Charlotte. We appreciate your interest in innovative, sustainable architectural solutions.